Hello, in this video I'm going to go over some slightly harder SUVAT questions or equations of constant acceleration, which bring out a few issues. The one thing I want to talk about, which we've been talking about quite a bit in class, is displacement and position. Most of the times these don't really matter, the difference between the two. Displacement is really the kind of distance in a particular direction. So if you're doing a vertical problem with gravity, you take any point upwards from some 0 point as positive and anywhere downwards as from some point as negative. And essentially position will be the same because you will just say, well, we're starting off at point 0. But what if we're not starting at point 0? Well, when would this kind of problem occur? When would we say it doesn't start at point 0? And the only time when this really might become a factor is when we've got kind of two particles kind of moving, and we want position to be an absolute point in space so that we can compare the two. If we've only got one, we can just say it starts at 0, and displacement and position is a kind of there's no real distinction between the two. And I think problem 2 is that we're going to do in a moment. We'll bring that out. Problem 3 is to do with when is also two particles, but in this time they're taken off at different times, not different places. So, and the first problem is really much more to do with just making sure we understand what we mean by displacement. Okay, so let's do the first problem. Okay, so the first problem is just we're taking gravity as we normally do unless told otherwise in most A-levels, I think all A-level specifications. In fact, we take gravity to be 9.8 meters per second squared downwards, and we've got something that's being projected upwards with speed 10 meters per second or velocity 10 meters per second. Okay, and obviously what's going to happen is it's going to go up and then back down again. Right, it says the time the stone is above 2 meters. Right, so the time it's taken to be above 2 meters. So what we need to do, again, we can take this as our 0 displacement or position. As I say, there's absolutely no distinction here between the two ideas. And it's going up 1.2. And we want the time, and in this case there'll be two of them, where the displacement is 2. And of course, the time we want above will be the difference between these two. If we call this T2 and this T1 when it comes, maybe the other way around would be better. T1 being the time it is at on the way up on its trajectory, and T2 being when it's on its way down. And then we can find the difference between the two. So here we go. We've got U equals 10, A equals minus 9.8, and S equals to 2, and we want T, or the two values of T. And so clearly the correct SUVAT is S is equal to UT plus half AT squared. Okay. And we can just put S in, which is 2 equals to 10 times T plus half times minus 9.8 T squared. And rearranging that, we get 4.9 T squared minus 10T minus 2 equals to 0. Now, we don't have to worry too much about solving that. I don't think that's a solve it. And we can actually use our, this should be plus 2 obviously. We can actually use our calculator to solve that. And we've got these two values. T2 equals to 1.816 and T1 equals to 0.2247. So the time above will be the difference between these two, which will be equal to 1.816 minus 0.2247, 1.59 to three significant figures, 1.59 seconds. Okay, so there it's just appreciating the idea of displacement or position, same thing in this context, being 2 meters above, finding the 2 times where it's 2 meters above, and then we can answer the question accordingly. The second part is just again about making sure that we get the signs right, because it's going downwards. We've got u as minus 5, so v is minus 5, so we've got u as 10, v as minus 5, t what we're asked to find out, and g equals to minus 9.8. So the appropriate SUVAT in this case is v is equal to u plus at. Okay, now v equals u plus at, you have minus 5 equals to 10 minus 9.8 t. So we can say 9.8 t equals 15. So t is equal to 9.8 divide 15. And that's equal to 0.53, so 653. So just did that question. You need to understand, particularly first part, taking care of directions and getting the idea of displacement. The displacement just basically means how far what it is from, positive or negative from a particular point in a starting point. And in this case, displacement and position are the same thing. Right, now problem 2 is the kind of problem we need to do when we need to actually look at where we've got different starting positions, and you might find it helpful if the starting position is different. You might find it useful to actually use this formula, S minus S naught is equal to ut plus a half at squared. So this just now enables us to compare the position of two different particles so that S kind of is consistent between the two. So basically, looking at the problem, that this is going to be useful. We've got something being projected upwards with 8 meters per second. Let's call that particle A. And we've got something being, I think, dropped 5 meters above. So it's 5 meters. So it's like we can think of this as a number line. So this is like position now, so that we're consistent between A and B. We could talk about the position of AB along the vertical line, and that's where the distinction between position and displacement is important, so that we can compare and we can, as appropriate, equate B and A for when they collide. Okay, so let's just do the problem then. Let's look at particle A first. Particle A is has initial speed 8, and remember the acceleration is always downwards. Our default is 9.8 meters per second squared. That's what we take it to in, I think all the A-level specifications do that unless told otherwise. So then we can just do, well, this one starting from the origin. So we can just say S is equal to 8 times t plus a half times minus 9.8 t squared. So that equals to 8t minus 4.9 t squared. So then let's look at particle B, and this is where this formula can be useful when it's starting at, because if we're going to use the formula so that we compare them, we really need S to mean the same thing. So S in this case is the same thing, but S naught is equal to 5, because that's where it's starting from up here, equals to UT, well that's naught times T, plus a half times by minus 9.8 t squared. So that gives us S is equal to 5 minus 4.9 t squared. Notice that the acceleration is negative in both cases because we're taking upwards as positive in this case for both particles so that we're consistent. So then we can equate these two, because the beauty of this now is that because we've set it up like this, the S basically refers to where it is along this number line. So we can then compare the two, and we can say that 8t minus 4.9 t squared is equal to 5 minus 4.9 t squared. So that gives us 8t equals to 5, t equals to 5 over 8, which is 0.675 seconds. So that's t, and so we can easily also work out what the height is. Okay, so we can work out the height. We can just put the value of t back into either one of these. Let's put it back into this one. So we've got the height will just be whatever the value of S is, and it should be the same either case. So the height is equal to 5 minus 4.9 times 0.675 squared, and I think that comes to 3.09. to 3 significant figures. It might be worth checking that comes to the same answer as if we put that into there. Okay, right, so that's where this formula comes in. It's really it's hard to imagine a situation where there's not two particles, where you're trying to compare the two and the positions of them, where you might want to use that. Okay, here's another type of problem. Here they're starting off at the same position, so the distinction between displacement and position really doesn't matter. But the thing is, here they're taking off at different times, so that's what kind of sets this problem about. And in this case, it says particle P is moving along a point O, and it started with speed 12 meters per second. Okay, and 1 second after P has been projected from 0, another particle Q is projected vertically upwards with speed 20 meters per second. I'm drawing it next to it because I can't draw them on the same thing, but they're actually in the same position. Okay, and we want to find out the distance, the time it takes for them to collide, and the distance of the points where P and Q will collide, and they're taking off from a different time. So let's consider P first. So we've got no problems with the position of the position here or displacement because they're starting off from the same point. We can talk about the P as being equal to, and we're using S equals ut plus half at squared. We can talk about P being, we've got u as 12, so 12t plus a half times minus 9.8 because the acceleration is downwards, 9.8 meters per second downwards, 9.8 meters per second times t squared. So we have SP is equal to 12t minus 4.9t squared. Right, and we can do a similar thing for Q. SQ. Now here's the thing here, because Q is being taken 1 second later, making sure we have the correct value of t. It's going to take 1 second less time to if we're comparing the times, it's going to take 1 second less for it to travel a certain distance. So in this case, the formula will be 20 times the time that Q has travelled, which is 1 second less than the time that P has travelled. So that's 20 times t minus 1 minus or plus a half times minus 9.8 times by t squared, t minus 1 squared. So we've got SQ is equal to 20t minus 20 minus 4.9, and let's expand the brackets whilst we're at it, t squared minus 2t plus 1. So we have SQ equals to, and we've got minus 9.8 t times by plus 2t there, so that's equal to 29.8 t, and we've got minus 20 and minus 4.9, so it's minus 24.9, and we've got minus 4.9 t squared. So when they meet, the displacement is the same from 0. Or they're in the same position, as I keep saying, doesn't really matter in this particular example. 12t minus 4.9t squared is equal to 29.8t minus 24.9 minus 4.9t squared, and in this case the 24.9t squared cancels, and we get 17.8t equals to 24.9. So that gives us t is equal to 1.40. It was 1.398 something, but 1.40 to three significant figures. Nearly done, but we want the distance as well, so we can put that into either of these two formulas. It would probably be easier to put it in this one. So the distance equals to S is equal to 12 times by this value here. I'm going to put it, I'm probably stored it on my calculator, 1.39 blah 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 t, that's our value of t, minus 4.9 times the stored value for t, 1.39 blah 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 squared, and I think to three significant figures that comes to 7.20. So there we go. We had three different types of problems. First one was, well, The first one was just making sure we understood what displacement is, and if it's two, and that there's two different times when a displacement would be 2 in this particular question. Second one was just to make sure that we took care of making sure that we can compare the positions of A and B, and we kind of use this formula, which might be helpful. And the third problem was all about really that the position wasn't really a problem or displacement. The problem was making sure that we could compare the two values of t for the two different particles. So just have to think through the problem. It's all about problem solving really. So there you go. Hope this video has been useful to you. Bye bye.